And we're back as we continue talking about probability. Our lesson today is called Fried Freddies. We're going to continue talking about different representations of data, and we're going to use those samples to help make predictions and estimate probabilities. So, Fried Freddies. If you remember from last time, we talked about chocolate versus vanilla. Danielle is surprised by the results of that survey. The reason she explains, she asked several of her friends, and the results were as follows. Many of her female friends chose chocolate, and the males were split pretty evenly. And overall, chocolate was more preferred over vanilla. So in this situation, chocolate was the most preferred. How would you explain to her that this data may be less valid compared to the data from the previous survey? Well, if we think back to what we did last time, in our chocolate versus vanilla argument, we saw that we had 14,766 surveys. And if we go back to Danielle's survey, there's only 47. So if you think back to the law of large numbers, we would say, the law of large numbers states that we need more data in order to make predictions. If we don't have enough data, it could be a random occurrence. So we need lots of numbers in order to make this true. So using a sufficiently large number of trials helps us estimate a probability of an event happening. If the sample is large enough, we can say that we have an estimated probability outcome for the probability of the event happening. If the sample is not randomly selected, only asking your friends, or not large enough, collecting 4 data points is not enough information to estimate long-run probabilities, then one should not estimate large-scale probabilities. Sometimes your sample increases in size over time. Below is an example of data that's collected over time, so that the estimated probability outcome becomes more precise as the sample increases over time. So here's our example that we're going to focus on today. Freddy loves fried food. His passion for the perfect fried food recipes led him to opening the restaurant Fried Freddy's. His 2 main dishes are focused around fish or chicken. Knowing he has also had to open up his menu to people who prefer to have their food grilled, which is healthier, instead of fried, he created the following menu board. Fried Freddy's. Choose dish, chicken or fish. Cooking preference, grilled or fried, $7.95. So let's see how well his business is in this manner. So after being open for 6 months, Freddy realized he was having more food waste than he should because he was not predicting how much he should have prepared in advance. His business friend Tyrell said he could help. What information do you think Tyrell would need? Well, I think I would need to know, what have I done? How much have I cooked? How much has he cooked of each food? And of each, how are we labeling that? Of each cooking preference. So, how much chicken is he making? How much fish is he making? How much is he grilling? How much is he frying? Let's look at the data. And I'm sure that's what most businesses do. They take a look at what they've done over time. McDonald's, how many quarter pounders of cheese should I have ready under the heat lamp? How many McChickens should I have? How many batches of fries should I have ready to go? At which times of the day? That's all kind of information that would be beneficial. So luckily, Freddy uses a computer to take orders, so Tyrell has lots of data to pull from. After determining the average number of customers Freddy serves each day, Tyrell created the following Venn diagram to show Freddy the food preference of his customers. So fish, you can see, makes up 45% of his food. And fried fish would be 15% of all of his sales, which would mean grilled fish is 30%. And fried non-fish, this would be fried chicken, 20%. And so what does that leave us with? 30, 45, 65. So this would be 35% in the neither category. So neither fish, neither fries, this would be grilled chicken. So maybe we want to organize that another way. Why don't you try organizing a 2-way table for this, or a tree diagram? And then we'll take a look at this in a little bit. So take the time to create one of those diagrams, and then we'll move on. So pause it now. Okay, so hopefully you had time to create a two-way table or a tree diagram to help organize that data a little bit, since the Venn diagram isn't always perfectly clear. So now we're going to take that information, and in order to make sense of our diagram, let's compute the following probability statements. So what's the probability that a randomly selected customer would order fish? Probability of fish equals, and then shade the part of the diagram that will model that. So go through and answer questions 3 through 9, and then shade in the diagram where we see that on our Venn diagram. Keep in mind that this is fried, and this is fish. Okay, so just sketch in where we see that information on the diagram. Pause the video and restart it when you're ready to check your answers. Alright, so hopefully you had time to make sense of the diagrams, but focusing especially on the Venn diagram, we were taking a look at these probabilities. So probability that you order fish. Well, fish is this whole circle here, and if we're taking a look at the whole circle, we added both those together, and we found that it was 45%. Probability was fried and fish. Remember, this was fried and this was fish. So it's the intersection of those two circles in the Venn diagram. So the intersection is the fancy name we use for it in probability, is this kind of upside down shaped U. It joins together fried and fish where they intersect. And that was 15% when we looked at our diagram between those two. 45 for fish total, 35 for fried total, but 15 together where they intersect. So the intersection of fried and chicken, in this case, is where those intersect. Well, chicken we know is outside the circles, or outside of this circle, rather. So everything outside of there that intersects also with fried would be right here, so that's 20%. And then the probability of selected customer want their fish grilled. So grilled and fish. So the intersection of grilled and fish would be right here. And that would be what we call the complement of probability of fried. So here is fried, and the complement is everything else from that. And actually, think about that. I said that one wrong. It's not the complement of fried fish. We'll talk about a complement in a moment. But forget what I just said about that. But anyway, grilled fish is everything that is fish and also grilled. So it's not part of the fried, but it's everything that's part of grilled and fish together. That would be 30%. Freddy serves 100 meals at lunch on a particular day. How many orders of fish should he prepare with his famous fried recipe? How many fried fish? Fried fish is 15%. 15% out of 100 is 15. Now here's the probability of a person to choose fish or fried. Okay, this is the union of the two. And here we use the U for union. Notice it's everything that's fish. Here's the fish circle. Here's the fried circle. It's everything that's included in there. So, the key thing is, we're just adding up everything that's together in these two circles. So in that case, it's 30 plus 15 plus 20, which is 65%. Now, the important thing as we're doing that is we need to make sure that we, if we're looking at a table, if we're looking at probably fish is 45%, fried is 35%, we've got a total of, what is that, 80% there? But we're really adding all these columns up in this row. So we're adding this one twice. So if we're looking at a two-way table, we'd have to add the total fish, total fried, and subtract out where the intersection is. So that's where the Venn diagram is a little bit more helpful. You can just look at everything there. And then probably they not choose fish or fried. Not fish, not fried is everything outside of there. So that'd be the complement, which I was talking about before. I think I'm saying it right this time. So the complement is, 1 minus, because everything adds up to 100%. So 100% minus the probability of fried union fish. will give us the probability of not fish or fried. So it's everything outside there. So complement means they add up to 100%. So here's a couple phrases that we're learning: the intersection, the union, the complement. There's some phrases that will help us as we start working through probability and getting your idea of what that means. A union B, everything in either of one of the sets. A intersect B, things have to be in both. It's the intersection of the two. The complement, or not A, everything outside of one particular unit, or any of those different ones that we look at there. But some other things that we want to keep in mind are the terms mutually exclusive. Two things are mutually exclusive if they don't contain anything. Let's take a look at some of those examples. Another phrase that we'll get is mutually exclusive events. Those are things that can't happen at the same time. So turning left and turning right, can't do both at the same time. Tossing a coin, heads and tails, mutually exclusive. Kings and aces are mutually exclusive because you can't have both on the same card. Not mutually exclusive, turning left and scratching your head, you can do both at the same time. Kings and hearts, because you can have both of those. So here's examples of Venn diagrams. Aces and kings are mutually exclusive, but hearts and kings are not mutually exclusive because there's an intersection where you can have both a heart and a king. That's just another thing that we need to know. All right, so we've gone through the lesson, gone through some terminology that we can use to help take a look at how we can, take a look at, how we determine, probabilities of different things and use different representations. So in your work that you can do in class, we'll talk about independent and dependent events. That's kind of mutually exclusive thing. And it's similar to mutually exclusive events in that, mutually exclusive are events that two can't happen at the same time. So independent and dependent. Independent means they don't happen at the same time. So for this first example, coin is flipped twice. First event is the first flip, second event is the next flip. So those would be independent of each other because what happens in the first coin doesn't affect my chances on the second coin. Dependent events would be ones where there's what am I trying to say? There's an effect on what you get in the first event that affects the second event. So like the bag of marbles, you get 3 blue, 6 red, 2 yellow. 2 marbles are drawn out. The first event is the first marble taken out. The second event is the second marble. So let's say I pull a blue marble out. Now I've got less of a chance to get a blue marble and a better chance to get one of the other ones. So those would be dependent events because probabilities change as it happens. So you'll work through that, and then you'll work more with the addition rule, interpreting Venn diagrams, and getting into more of the terminology for the intersections and unions. Working more with that, creating a two-way frequency table, and then getting into equivalent ratios and proportions, which we can take our probabilities and use proportions to make predictions. So you work through that, and I can answer any questions you might have in class.